video, we are going to explain about the project title, Classification and Forecasting of Water Stress in Tomato Plants Using Bioristor Data. Introduction. Water stress and drought pose significant challenges to agricultural productivity, impacting plant growth, food production, and global food security. Recognizing the urgency of addressing these issues, this project focuses on advancing our understanding of water stress in tomato plants and developing innovative solutions for efficient water management. The primary objective is to characterize, classify, and forecast water stress in tomato plants. The project acknowledges the pivotal role of water conditions in influencing the health and yield of tomato crops. In pursuit of accurate and timely information, the project leverages a novel sensor known as the Bioristor to collect in vivo real-time data. This approach enables a dynamic and responsive assessment of the water status within tomato plants. Early detection, characterization, and prediction of water stress and drought conditions are recognized as crucial components for agri-tech decision support systems. Proactive measures based on timely information are essential for promoting sustainable water management practices. Harnessing the power of machine learning and artificial intelligence, the project aims to develop predictive models capable of accurately foreseeing water stress in the short to medium term. This technological approach showcases a commitment to advancing agricultural practices through computational methods. With the ultimate goal of practical application, the project seeks to classify and forecast water stress using the Bioristor data and diverse AI models. The envisioned outcome is the development of a smart irrigation system that optimizes water usage, enhances crop yields, and contributes to global food production. Objective. The primary goal of the project is to address the issue of water stress in tomato plants. This involves three key tasks: characterization, classification, and forecasting. These tasks are accomplished by leveraging real-time data collected from the Bioristor sensor, a specialized tool designed for monitoring physiological conditions in plants. Artificial intelligence models are employed as analytical tools to process this data and provide insights into water stress patterns. To achieve the goal of characterization, the project utilizes classification models, specifically decision trees and random forest. These models are applied to the real-time data obtained from the Bioristor sensor. The objective is to differentiate and categorize the various stress stages experienced by tomato plants. This step is essential for understanding and classifying the dynamic water stress conditions in the plants. In addition to classification, the project employs recurrent neural networks (RNNs) to predict the future water stress status of tomato plants. The prediction is conducted in two scenarios: binary, categorizing plants as either water stressed or not water stressed, and a more detailed four status scenario. RNNs are particularly suited for sequential data, making them suitable for forecasting dynamic conditions over time. The project undertakes a comprehensive evaluation of the developed models. This includes assessing key performance metrics such as accuracy, precision recall, and F measure. These metrics provide insights into the effectiveness of the classification and prediction models. Furthermore, the project aims to explore the practical application of the Bioristor sensor and AI models in real-world smart irrigation scenarios. This suggests a practical orientation with the intention of translating research findings into actionable solutions for smart and efficient irrigation practices. Software and hardware requirements. Software requirements of the project are: software is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. In this initial step, necessary Python packages and libraries are imported. These include popular machine learning libraries such as TensorFlow or PyTorch for building the model, as well as data manipulation and visualization libraries like Pandas and Matplotlib. Exploring the dataset, Bioristor sensor dataset. This module involves gaining an understanding of the dataset acquired from the Bioristor sensor. Exploration includes inspecting the structure of the data, checking for missing values, and visualizing key features. Understanding the dataset is crucial for informed decision making during the subsequent steps. Data pre-processing. This step involves preparing the dataset for model training. Key pre-processing tasks include shuffling the dataset to ensure randomness, normalization of data to scale features, and handling any missing or inconsistent values. Proper data pre-processing is essential for improving the model's performance. Split the dataset to train and test. The dataset is divided into two subsets, one for training the machine learning model and another for testing its performance. This separation allows the assessment of the model's generalization on unseen data. Building the model. The machine learning model for classifying and forecasting water stress in tomato plants is constructed in this module. Depending on the project's requirements, this involves using algorithms like decision trees, random forest, or neural networks tailored to the specific nature of the dataset and the problem. Training the model. The model is trained on the training dataset using the relevant machine learning algorithm. During training, the model learns to recognize patterns and relationships within the data that enable it to make accurate predictions. Flask framework with SQLite for sign up and sign in. This module involves setting up a web framework using Flask to create a user interface. Additionally, an SQLite database is integrated to manage user sign-up and sign-in functionalities. Flask is a popular choice for building web applications due to its simplicity and flexibility. User upload an image for analysis. Users interact with the application by uploading an image relevant to the project, a photo of a tomato plant. This image serves as input for the water stress classification and forecasting model. The given input is pre-processed. The uploaded image undergoes pre-processing to prepare it for analysis. This involves resizing, normalization, or any other transformations required to align the input with the model's expectations. The trained model is used for predicting the result. The pre-processed image is fed into the previously trained machine learning model to predict the water stress status of the tomato plant. The model leverages the learned patterns from the training data to make predictions on new, unseen data. Final outcome is displayed through front end. The results of the predictions are presented to the user through the front end of the web application. This includes displaying the water stress classification, forecasting results, and any additional relevant information. Algorithms used. To implement this project, we have utilized the following algorithms. The first algorithm is decision tree with Gini index. Decision trees are a popular machine learning algorithm for both classification and regression tasks. The Gini index is a criterion used to evaluate the impurity of a dataset. In the context of classification, decision trees with Gini index work by recursively splitting the dataset based on features to maximize the separation of classes. The Gini index measures the probability of incorrectly classifying a randomly chosen element, and the tree is constructed to minimize this index at each split. Decision tree with information gain. Similar to the Gini index, information gain is another criterion used in decision trees, particularly in ID3, iterative dichotomizer 3, and C4.5 algorithms. Information gain is based on the concept of entropy, which measures the disorder or uncertainty in a dataset. Decision trees with information gain aim to create splits that maximize the reduction in entropy at each step, leading to a more organized and pure classification of data. Random forest. Random forest is an ensemble learning method that combines multiple decision trees to create a more robust and accurate model. It introduces randomness by training each tree on a random subset of the data and considering a random subset of features at each split. The final prediction is then obtained by aggregating the predictions of individual trees often resulting in improved generalization and reduced overfitting compared to a single decision tree. LSTM, long short term memory. LSTM is a type of recurrent neural network RNN designed for sequential data. In the context of the project, LSTM is used for its ability to capture and remember dependencies in time series data. If the dataset includes temporal aspects or sequences related to water stress in tomato plants, LSTM can effectively model these patterns. This makes it suitable for predicting the future water stress status of the plants based on historical data from the Bioristor sensor. As an extension, we applied deep learning model to produce a more robust and accurate final prediction. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis we have accuracy score, and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis we have precision score, and on the y-axis we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is recall comparison graph. On the x-axis we have recall score, and on the y-axis we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the F1 comparison graph. On the x-axis we have F1 score, and on the y-axis we have algorithm name. F1 score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm, which is performing best in all the performance metric, will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flash framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flash framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered myself. So click on this link. So here we need to enter the username and the password which we have registered and then click on login. We have logged in successfully. So here we need to upload the tomato plant image, and after uploading the image we will predict whether tomato is drought stress or no drought stress. Click on choose file. I'm selecting the first image here. Click on open button. Now click on upload button. So here we can see the outcome, that is tomato is drought stress. Let us upload some more images. Click on choose file. So here we can see the outcome, that is tomato is drought stress. Let us upload one more image. I'm selecting the last image. Click on open. So here we can see the outcome, that is tomato is no drought stress. In this way, by uploading the image, we can classify whether tomato is drought stress or no drought stress. Click on sign out button here. The conclusion of the project. This point indicates that the project achieved its primary objectives of characterizing, classifying, and forecasting water stress in tomato plants. It utilized real time data from the Bioristor sensor, suggesting a dynamic and responsive approach to monitoring plant conditions. The integration of various artificial intelligence models implies a comprehensive and sophisticated methodology for analyzing the data. Decision trees in random forest, both popular classification models, were successfully applied to differentiate between different stress statuses of tomato plants. The mention of good results in terms of accuracy, precision, recall, and F measure suggests that the models effectively identified and classified the water stress conditions. This indicates the reliability and effectiveness of the chosen machine learning techniques. Recurrent neural networks (RNNs) were employed to predict the future water stress status of tomato plants. The mention of considering both binary and four status scenarios indicates a comprehensive approach to prediction. The term promising results implies that the RNNs demonstrated the ability to capture temporal patterns in the data, providing reliable forecasts for different stress scenarios. The project hints at the practical application of the Bioristor sensor and AI models in real world smart irrigation settings. The project underscores the significance of predicting water stress and acknowledges its impact on plant growth, food production, and food security. By emphasizing the potential applications of the Bioristor sensor and machine learning techniques, the project suggests that these tools can contribute to optimizing irrigation practices. The overall implication is that improved water stress prediction can lead to enhanced agricultural outcomes, contributing to addressing global food security challenges.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.